Let's talk a little bit about derivatives, especially in the context of what we'll be using when we talk about chemistry and physics. First, a derivative is a descriptor of how one variable instantaneously changes as you change another variable. In math, this is often shown first as calculating an average slope of a curve and making the step size smaller and smaller until the slope creates a line tangent to the curve. I won't get into the details of exactly how this is done, but this is the idea behind the derivative. Derivatives are represented in many different ways, and this can sometimes become confusing, especially when we switch between representations. If I have a function of one variable, we often represent this as a simple dy over dx, meaning that we are taking the derivative of some function represented by y with respect to x. However, using this representation may be less useful when we start dealing with functions of several variables. Let's say that I have a function where a is equal to x plus y plus z, and I ask you to take the derivative of a with respect to x. To do this, you would need to know how y and z change with a change in x, but perhaps you want to keep y and z constant. Instead, we can ask for a partial derivative of a with respect to x, and when we do this, we will treat the values of y and z like we would treat a constant. To represent a partial derivative, we use this oddly shaped d. Often when we use a partial derivative, we may put a subscript after it listing the variables that are held constant. Next, let's talk about mathematical manipulations with derivatives. Once again, the derivative simply asks us how an infinitesimally small change in one value leads to a small change in another value. We write this like a quotient. However, just like a quotient, I can multiply by the denominator on both sides for it to cancel out. This contains all of the same meaning, and means that for an infinitesimally small change in y, we get the value of the slope multiplied by an infinitesimally small change in x. When we do this to a partial derivative, we often revert back to using the regularly stylized d, which can be a bit confusing. There is one last type of d that we will encounter, the inexact differential. The two main ones that we will see are used regarding heat and work. Heat and work are not state functions, which, unlike energy, they are not path independent. This will be a topic covered in more detail in a future video, but it reminds us that these variables are path dependent and typical thermodynamic manipulations we make may not work. The last type of change we will see is a delta in front of our function. This is no longer meaning an infinitesimally small change, but instead it could be a large change, something that we could measure from our function that we've created. Finally, because it fits well here, I want to introduce something known as the total differential, which is used when dealing with a function of multiple variables. Say I have a function a with variables x, y, and z, and I ask for the total differential of a dA. This total differential is equal to the partial derivative of a with respect to x multiplied by dx, plus the partial derivative of a with respect to y multiplied by dy, plus the partial derivative of a with respect to z multiplied by dz. This total differential is used again and again in statistical thermodynamics, and we will see it often. Thank you for watching this video detailing derivatives and the different forms that they can take. If you enjoyed this video, please like and share this video as it helps considerably in increasing outreach. If you want to see more videos on chemistry and physics topics, please consider subscribing to the channel. I have linked my Patreon page in the description below, and if you would like to support educational content like this, please consider donating. Finally, please comment down below if there is something you feel like I could make more clear, or if there are other topics that you would like me to cover. Thank you.